histograms and so on. And then we also talked about the normal distribution, which you might have covered in probability 1. And we also talked about the binomial distribution, which again you might have covered in probability 1. Right, this week I'm going to talk about 3 different things. One is called the central limit theorem, which you might have covered this in probability 1, I don't know. And the second one is called 2 sampling distributions. One of them is called the chi-square distribution. The other one is called the student's t distribution. Both of them are referred to as sampling distributions. Okay. Right. So let me change the camera. So here we go. Okay. Hope you can see this. So this is the slide on the central limit theorem, which says that if you have a random sample from a population with population mean equal to mu and population variance equal to sigma squared, then this statement here is true, right? As I said, you might have seen this before. I don't know. You might have seen this result before, but it says basically that you take x bar, which is the sample mean, and subtract the population mean and divide by this, which is known as the standard error. Then this approaches the standard normal distribution as the sample size goes to infinity, right? Now, I think some of you are still confused about these two. This is the sample mean, and this is the population mean. They are 2 different things. The sample mean is associated with the sample, whereas the population mean is associated with the population. They're not the same thing, because usually the population is something that we cannot access. Like suppose you want to find the average age of all people in the UK. Obviously, I mean, there are millions of people in the UK, so you can't access the population. So you need to draw a sample, usually like 100 or 1,000, and then record their age, right? So the sample mean will be the average of the ages for the people you selected, whereas the population mean is the average age for the entire population, which is we don't know what that will be, right? Okay, so this is the central limit theorem. I'm sure you know. And okay, now a model based on the central limit theorem. Now suppose your sample size is large enough that this is approximately equal to this, right? So I mean, in statistics, as I said, in statistics, we usually suppose that anything that is greater than 25 is large enough, right? So if this is the case, then you can work out after some math, I mean, which I'm not going to go through. I mean, if you have difficulty following this math, please contact me 24/7. If you do this math, then you come to this stage here which says that the CDF of the sum of the random variables can be approximated by this, where phi denotes the CDF of the standard normal distribution, right? So this is an approximation for the CDF of a sum of IID random variables following any distribution, right? Now, by the way, if you have any questions, use the chat box, right? Use the chat box, or you can use, yeah, that's the best way to do it.
What?
IID means independent and identically distributed.
Right? Morning. Because I'm in the middle of a lecture. I wasn't.
Sorry. IID means independent and identically distributed, guys. That's what it means. All right, now using this result, this result is very, very useful, because one example of this is as follows, right? Now, suppose you have IID Bernoulli, then you guys know from probability 1 that the sum of IID Bernoulli is a binomial, right? So if these are from Bernoulli 0.2, then the sum of IID is binomial with these parameters. So you can use the previous result, which I mentioned a minute ago, to compute this probability, which becomes this, right? and it turns out to be equal to something like this. I hope you followed this example. If you did not, just please go through it, and if you have problems, just let me know. Right, the next thing I'm going to talk about is sampling distribution. Sampling distribution are distributions that arise as functions of data. I mean, in statistics, there are many sampling distributions, but in this course, I will only talk about two. One is called the chi-squared, denoted by this. The other one is called students T, denoted by this, right? I'm disappointed with the number of people turning up for classes, guys. What's the problem? It's not just because it's recorded, it's not an excuse for not turning up. Okay. All right, now let me start talking about chi-squared first. A chi-squared random variable has this as the density function. This is where A is referred to as the degree of freedom parameter. Okay, and X is positive, that is defined on the positive domain. And the typical shape of the density is something like this, right? And these are the commands in R for computing the PDF, the density function, and the CDF, right, cumulative distribution function. All right, and I'm going through this stuff quickly because I asked you guys to watch this and ask, right, and the percentile of a chi-squared is denoted by this. So this is the point on the x-axis of the density function, so that the area to the left of it is alpha. So this area here, this area is equal to alpha, and this is the point known as the percentile of chi-squared with a degree of freedom and corresponding to an area of alpha. So there are tables for reading these, which are this one here. This is a table, this is a table for reading values of this, right? And I have shown you how to read two particular values, this one and this one, right? Okay, so this is the table. I hope you followed my video about how to read this table. If you did not, please, contact me 24/7. These are some properties of a chi-squared distribution. So if you have a variable x that has a chi-squared with a degree of freedom, the expectation is a. The expected value of x is a. The variance is 2 times a. And this is an important property. This property is very, very important. We will use this multiple times in this course. Now, what it says is that if you have IID normal with, I will come to that hang in a minute. The two tables are on the website, Mikhail. I mean, the two tables are actually on the website. They are actually on the website. You should be able to see them on the website. All right. Okay. In property 3, let me tell you, if these are IID with normal and zero mean and variance sigma squared, then this statement is true. Now, if you look at the left-hand side, what you have is a function of data only. And if you look at the right-hand side, what you have is a chi-square distribution. And this property is the reason why the chi-square distribution is a sampling distribution, because you have a function of data. You have a function of data that follows the chi-square distribution. Remember, at the beginning of a sampling distribution, I told you that a sampling distribution is a distribution that arises as a function of the data, and that is what you see here precisely, right? Now, okay, coming back to the question of hang. Now, here I'm assuming that the mean is 0, but this statement is also true if the mean is not 0. I will come to an example later on where the mean is not 0, you can still apply this statement, right? Even if the mean is not 0, right? So that's property 3 is very important. Okay. Property 3 is very important. Okay. Now, property 4 is that if you have two independent chi-squared variables, then their sum is also chi-squared with a plus b degree of freedom. And if you have x is standard normal, then x squared is chi-squared with 1 degree of freedom. And property 6, somebody is asking about that. All right, property 6 and property 3 are very different. They are not the same, guys. Okay, let me show you why. Let me show you why. You see, in property 3, we are taking the deviations of xi from the sample mean, whereas in property 6, we are taking the deviations from the population mean. So these two are not the same. Right here, if you have IID normal, then this has a chi-squared with n degree of freedom, whereas here, it has chi-squared with n minus 1 degree of freedom. You see the difference? The difference is that in property 3, the deviations are taken with respect to the sample mean, whereas in property 6, the deviations are taken with respect to the population mean. Right, so there's a huge difference between these two, right? And you must be careful which to use what, right? Which to use when, okay? All right, so this is an example on chi-square distribution. All right, the next one is student's t distribution. There's a story about this. This distribution is due to William Gossett, who's a British statistician who worked for Guinness, the Irish beer company. And the thing is that one of the policies of this company is that you're not allowed to publish your research on the public domain under your own name. So he published his results under the name student, which is, obviously not his name, but so that's why this distribution is referred to as student's t distribution, right? And once again, there's a parameter a, which is referred to as the degree of freedom parameter, and x, the domain of this density is from negative infinity to plus positive infinity. Okay, right. Okay, now shape. You should draw the shape of the normal PDF, the standard normal PDF, and the student T PDF. This is the student T PDF in red, and the normal PDF in black, right? You see, both of them look very similar, but there is a huge difference. That the PDF of the normal decays to 0 much faster than the PDF of the student's T. So in other words, the PDF of the student's T decays to 0 much slower than the PDF of the standard normal, right? Okay, right. So these are the commands. This is a command in R for computing the density of a T distribution with the degree of freedom equal to 2. And this is the command for computing the CDF of student's T with degree of freedom equal to 2, right? Right, next, the percentile. Yeah, the percentile of a student's T variable is defined by this statement. So once again, what this means is that you're looking for a point on the x-axis such that the area to the left of this point, that is this area, is equal to alpha, right? So this point must have an area of alpha to the left of it, right? That's what this statement here says. And once again, there are tables for reading the percentile, this value, and I have included a copy of this table here. This is the table for reading values of this percentile, right? And these are some examples on how to read the table. Now, once again, the copy of this table is on if you go to the course website, I'm sure all of you know where it is, you will see a copy of this table, right, on the course website. Okay. Right, next, there are some properties of a T variable. The first property is that the expected value is 0. The second is that the variance is given by this a divided by a minus 2. The third property is that it approaches a standard normal variable, that the student's t variable approaches this as a, the degree of freedom approaches infinity. Now the fourth property is the most important one of all. Now if you have IID, normal with 0 mean and variance sigma squared, then this statement is true. Now what this says is where x bar is the sample mean and s is the sample standard deviation. Okay, now if you look at the left hand side, this one, you see what you see is a function of data. The left hand side is a function of data only. And the right hand side is a distribution. It's a distribution which is the student's t distribution. And hence, because a function of data follows this distribution, the t distribution must be a sampling distribution. Can we assume that the sampling distribution is, I don't understand your question, sir. Can we assume that sampling distribution is just a function of which describe how the samples, can you rephrase your question, sir? I cannot understand your question. All right, I mean, what I mean here, sir, is that on the left-hand side, you see a function that involves only the data, nothing else, only the data. And hence, the distribution of this, which is this, must be a sampling distribution. That's what I'm saying, okay? Okay, I hope you guys follow that. All right. And finally, this is an example on the t distribution, right? Okay, and this completes. Okay, now what I'm going to do in the remaining time is to do some examples as usual. I mean, I've got plenty of time remaining, so I hope to do at least quite a few examples today. All right, let's start with this example 1, which is example 1. Let's start with example 1, guys. All right, so suppose you have IID. IID means, by the way, independent and identically distributed Poisson variables with parameter lambda. And the question is to find the probability that the sum of xi is between A and B. Right, now, let's see how we can do this. Now, I'm gonna start with this statement here. Thank you, Matthew, for pointing out. If you guys look at the message from Matthew Taylor, it says that there is a link called formulas on the course website. If you look at that link on pages 30 to 33, it gives the table. Right, okay. All right, now let me compute this guy, all right? So what I'm gonna do is, if you don't follow this, just let me know, okay? So you see what I've done? I have divided each term by n, right? Okay, now, this guy here is the sample mean, right? Right, okay. And then what I'm going to do now is I'm going to use the central limit theorem. In order to use the central limit theorem, I need to, all right, before I, okay, let me do it slowly.
Solution, let's find the general of the differential equation y.
Hello, sir, we are all muting. You're on a class. You see what I'm done, what I'm doing, guys. I have subtracted mu. Mu is the population mean, and divided by the standard error on for each of the three terms. Right now, mu. Remember, mu is the population mean. In other words, the expected value of x. Now, x we know has the Poisson distribution with parameter lambda, right? So I'm sure you know from probability 1, which you took last semester, that the expectation of a Poisson variable is lambda. And sigma squared is the variance of x. And the variance of a Poisson variable is also lambda, right? So sigma is equal to the square root of lambda, right? You follow me, guys? So let me put this in a box. Okay, now what I'm going to do is I'm going to replace the mu and the sigma by lambda, right? So sigma is going to be square root of lambda, by the way. So it's square root of n. All right, you follow me, guys? Please let me know if you're done. Right now, in the next step, I'm going to use the central limit theorem, which I talked about earlier today. Right, by the central limit theorem, if n is large, we can approximate this, the middle term, by the standard normal. So this will become this is actually an approximation, okay? Approximation. All right, guys. Okay, now this you can write as the probability that a normal variable, standard normal variable, is less than or equal to right? Okay, minus the probability that right? And finally we can write this as, this term can be written as phi. Remember, phi denotes the CDF of a standard normal variable, right? And this term here can be written as all right, so this completes example 1. Are you guys okay with this or no? So what I have done in this example is to find, when you have a sequence of IID Poisson random variables with parameter lambda, I have shown you how to use the central limit theorem, to find the probability. The last bit is this one, guys. This probability here can be written as the difference of these two, right? And this probability here is the CDF of the standard normal at y it becomes n01. Yeah, the reason it becomes n01 is because of the central limit theorem. Okay, let me go back to the big. Remember, guys, I don't know whether you can see this clearly, but this is the central limit theorem, which says that x bar minus the population mean divided by sigma by root of n approaches the standard normal as n goes to infinity. So what I have used here, guys, is x bar minus the population mean, which is lambda, right, divided by sigma by root of n, which is this, right? So according to this must be close to this if n is pretty large. So if we assume that n is pretty large, then this or this must have an approximate standard normal distribution, right? All right, and that's what I have said here in this step here, that we can approximate this probability by this probability, right, if n is large, right? I mean, n can never be infinity, but if n is large, like say 30, I mean, in statistics, anything about 25 is considered large. So if n is a large number, then yes, that's right. Yeah, you are right. Yeah, it applies to all kind of distribution. As long as you can put it in this form, you can apply the central limit theorem to all kind of distributions. Yeah. All right. Any other questions, guys, on this example? Example 1. Hello, guys. Talk to me. Are you okay with this example 1? Yeah. Okay. Okay. Let me go to the next example, which is example 2. Example 2 is this one. All right. Excuse me. Suppose you have a random sample from normal with mean 1 and variance 1, and we want to find A and B such that the probability that the sample variance is between A and B is 0.95. John, I just explained what's the difference between 3 and 6 in chi-squared nodes. I can go through it again, but let me finish this example, John, first, and then I will explain that over again, okay? Maybe you missed that part, I don't know. So we start with this statement, okay, which is the same as saying that yeah. And this is the same as saying that I'm going to multiply everything by n minus 1. So this is going to be all right. Okay, you see what I've done? Okay, the next thing I'm going to do is I'm going to divide by sigma squared. Now, if you look at this, we have a mean of 1 and a variance of 1. So sigma is 1. Sigma squared is 1. So there's nothing to divide by. All right, now I'm going to use the result I talked about a few minutes ago. Let me show you. It's this result here. This you may recall just a few minutes ago I mentioned that this guy has this distribution, right? Okay, right. So using this result, you can say that this, right, right? You follow? Yeah. Okay. Now, okay. Let me at this stage it's really helpful to actually draw a picture. Okay. Let me draw a picture of the PDF of chi-squared with n minus 1 degree of freedom. Typically, it looks something like this. right? This is a typical shape, right? And now what we are looking is, we are looking for 2 points. This is the first point, this second point, that the area between these two is 0.95. So it could be this point and this point here, right? And we want the area between these 2 points. In other words, we want this area, right? We want this area to be equal to 95% of the total area. Remember, the total area must be 1, right? Okay. So now the question is how to choose these 2 points so that this area is 95%. One way you can do it, I mean, there are multiple ways you can do this. One way is to take this area here, take this area to be 2.5% of the total area, and take this area to be 2.5% of the total area. All right, so the total area is it is sigma squared, but sigma squared is 1, sir. I mean, sigma squared. If you look at this, your sigma squared is 1. So you're multiplying by 1, so it doesn't make any difference. All right, I will try to do as many examples as I can. So let me carry on with this. All right, this is 2.5% and this is 2.5%. So you can take this to be chi squared with n minus 1 corresponding to an area of 0.975, right? And you can take this to be chi squared n minus 1 area of 0.25. You see, I mean, a minute ago, not a few minutes ago, I told you, I talked about the percentiles of a chi-square distribution. A percentile is a point that covers the area to the left. So 0.025 is the area to the left. And over here, the area to the left of this point is 0.975. All right. So this point must be this, and this point must be this. All right. So in other words, what we are saying is that n minus 1 times a must be equal to, it's not necessary, Mikhail. It's not, I mean, it's not necessary that they must be equal, but for convenience, I'm just doing it for convenience, Mikhail, right? So, yeah, I mean, you're right. I mean, there are infinitely possible answers for this kind of question, right? But one way to answer this question is to choose these 2 areas to be equal, but they don't need to be, right? So what I'm saying is that this n minus 1 times a must be equal to this, which is this, and n minus 1 times b must be equal to this, which is this, right? And hence, to answer the question, a must be equal to 1 over n minus 1 times, right? And b must be equal to okay. All right, so this completes example 2. Are you okay with this, guys? Okay, thank you, guys. Okay, so that's example 2 now done. Example 1, example 2 done. Next example I'm going to do is example 3. What was the second, Sakina? What do you mean, what was the second? I don't understand your question, Sakina. What you mean, b equal to this? Yeah. Can you come again? You said that there were two ways of going through it. No, I mean, well, Sakin, what I'm saying is that this is one way of doing it, but there are multiple other ways you can do it, right? I mean, in this solution, I have taken these two to be equal, these two areas to be equal, right? So, but you can do it in multiple other ways too. Right, now, example 3. This is example 3. You have IID from a normal distribution with 0 mean and variance sigma squared. We want to find the probability that this is S, guys, okay, not 5. My handwriting is not good, right? Okay. Okay. Let me get back to property 6. You cannot apply property 6 here, sir, because property 6 talks about deviation from population mean. I think Matthew also asked, I mean, earlier somebody called Matthew asked the same question. I'm trying to find where it is. This is property 3. You can only apply property 3 to this question because the property 3 talks about deviation from the sample mean. Whereas property 6 talks about deviation from the population mean, which you can't use in this question because the sample variance talks about, this is property 6, guys. Yeah, here we are. This is property 6. So you see, this is deviation from population mean, whereas this is deviation from the sample mean, right? So these two are two different properties because this is the one you can use for the example I did because the sample variance is defined in terms of this. Yeah. Okay, and this has a chi-squared with n-1 degree of freedom. And when you take the deviation from the population mean, it has chi-squared n. These are two different properties, John. Yeah, it is n here and n-1 here. I mean, there are proofs for this. I don't want to go through the proofs, right? This is n here, okay. All right, let's start with example 3, right? So here, S, this is S, guys, not 5. Now, you know that one of the properties I mentioned in the normal distribution video last week is that if you have, I don't know whether you remember, if you have x1 to xn IID, right, normal with 0 mean and variance sigma squared, then x bar, the sample mean, is normal with, do you remember this property, guys, or not? This is a property I mentioned in the video on normal distribution last week, right? If you don't remember, it's okay. Please try to look at it. All right, now this will become okay using this property. This is equal to this, right? Okay, now the next thing I'm going to do is I'm going to make this 1. In order to make this 1, what do we need to divide by this, right? Sigma squared by n, yeah. That's the property, sir. Just please look at the video last week on normal distribution. It's a property I mentioned in the video last week. Please look at it. Okay. Right. All right. Now, you see what I've done here? I've divided by sigma by root of n and multiplied by this. The reason I have done this is because this, when you divide this by this is going to become a standard normal. So this will become the probability that sigma by root of n times standard normal is less than S, right? Okay, now the next thing I'm going to do, is this. You may remember, if you look at the t distribution, one of the properties I mentioned in the t distribution is the following. I'm trying to find out where it is. Just a minute. Give me a sec, guys. If you look at the one of the properties of the T distribution, I mentioned a few minutes ago. Oh, still can't find it. Oh, here we are. Okay, I found it. Okay, this is. I'll come back to that in a sec, guys. Okay. Excuse me. Okay, just a minute. Just a minute, guys. So what the next thing I'm going to do is there's no need for me to. All right. I mean, I think I done something unnecessary here. That there's no need for me to. Okay, let me go back to the previous step. Okay. All right. So let me skip these two. I don't need these two steps here. I'm sorry about this. I don't need these two steps. Right. Let me go back to the previous step. So this becomes this, right? Now the next thing I'm gonna do is I'm gonna do this, right? Right now, because of the property that I mentioned here, because of this property, right? Because of this property, this guy here on the left-hand side must be a t variable with n minus 1 degree of freedom. All right. So what you have is, I know this is where I don't know whether it denotes the CDF. Please let me know if you follow this or not. Please let me know. So I'm sorry, you don't follow. I'm sorry, I messed up at the beginning because remember this is the property I'm using, which when you have IID normal with 0 sigma squared, this follows the T distribution with n minus 1 degree of freedom. Now, this is x bar, right? This is x bar, right? So it's x bar divided by s less than 1, right? Yeah, it is the sample mean. Yeah, John, yeah, you are right. So this is, I mean, I should have called this x bar. Yeah, this is basically x bar. The one in the top is x bar. So x bar divided by s is less than 1, which implies that x bar divided by this is less than root of n, right? Okay. Now, dividing by root of n is the same as multiplying, because you remember, I'm dividing the denominator by root of n, Ella. Sure. Yeah, so dividing the numerator by, denominator by root of n is the same as multiplying by root of n. So that's what I'm doing here. Mikhail, I've got one more question. Well, I will get back to the example in the video. Trying to get to that, just a minute. The example in the video is this one here. This is the example I did in the video, if you may recall. Here is the same thing, guys. This guy here, Mikhail, is the x bar. It's the distribution of x bar, right? X bar has a normal distribution with 0 mean and variance 1 over n, right? So it's the same argument as in this example, Mikhail, right? Yeah, that's right. Yeah, because in that example you have to subtract 1 because in order to make the mean zero, right, you need to subtract 1. Otherwise, but in this example I don't have to do that because the mean is already 0. You see, if you look at the question here, the mean is already 0 here. So I don't have to subtract 1 or anything like that. How by, okay, one more question here. Okay, when you subtract 1 from this, Mikhail, right? When you subtract 1, this becomes this minus 1, which becomes this. I'm sure you know, I think this is a question some people asked me before. If you have x, a variable x or whatever, which has a distribution, say, mu sigma squared, right? Then x minus 1 is also normal with mu minus 1 sigma squared. I'm sure you know this property, or don't you? This is what I have used in this example. This is what I have used because x bar has this distribution, guys, right? Yeah. When you take away 1, it becomes this. Yeah. All right. Okay. All right. So any other questions on this example? This is example 3. I messed up a little bit here, but these 2 steps, we don't need them, right? We don't need these 2 steps. It's just confusing. So you can go from this directly to this, right? And then this, and then this, right? All right, so that's example 3. So we've done 3 examples today. One, I was gonna do 4 examples, but I don't know whether I have time or not. I mean, I was gonna do one more example today, but maybe I can do it now. Maybe if you can give. This is the bottom of the page, ma'am. This is the bottom of the page, yeah. I mean, I will post a copy of it in a minute. I mean, on the course website, you'll be able to see what is on the bottom. All right, okay. All right, so this is example 4, guys. I was gonna do in a minute. So maybe I would do it quickly, if you don't mind. Okay, so this is, you have geometric variables with parameter p. So the first thing I'm gonna do is I'm gonna divide by n. Sorry for taking your time, but I hope you don't mind. I hope you don't mind. Okay, now this becomes a over n. This is x bar b over n. Right, the next thing I'm going to do is I'm going to subtract I would like to see more of you. I would like to see more of you coming to the classes, guys. It's not all right now. Now for the geometric distribution, I don't know whether you know that the mu is the expectation of x is equal to p, and sigma squared is the variance of x is equal to 1 minus p over p squared. So sigma is equal to 1 minus p over p squared, the whole thing square root, right? Let me put this in a box, right? Okay, now the next thing I'm gonna do, yeah, I always do that, Joe. I always upload all the scan notes every time after the class. I do that every time, every day. I mean, every after review session every day. So mu is p, sigma is right. This is all right. Okay, this is what you get. Now, using the central limit theorem, CLT, this is standard normal, right? So this becomes the probability that, oh, you're right. You're right, so it's 1 over p. Yeah, you're right. I'm being stupid. I don't know. You're right. Thank you, Robert. Thank you, Robert. It should be 1 over p, not p. The mean of geometric is 1 over p. You're right. Thank you, Robert. Thank you. Yeah, the mean of a geometric variable is 1 over p, not p. I have corrected that. I have corrected it now. All right, so finally, if you do the rearrangement of everything, this will become phi . All right, so this completes example 4. I hope you followed this. Right, so, okay, guys, any questions on this, guys? On the 4 examples I've done today? Thank you, guys. So finally, please could I ask all of you to complete the week 2 feedback form, which you can find in the Blackboard. If you haven't done so, could you please? I've been nice to you guys. I mean, I've been upload. Everything is recorded for you. I mean, all the examples are recorded. All the tutorials are recorded. I would really appreciate if you could kindly complete the week 2 feedback as soon as you can by going into Blackboard. Thank you so much, guys. So I see you in the computer tutorial today from 4 to 5 or 5 to 6. All right. Take care and have a good day.